Okay, this is 14.7.10. Once again, a max-min problem, although this one's a word problem, so I'll have to build the functions. The bottom of a box costs 2 times more than the sides or the top by area. We want to find the dimensions that give the lowest overall cost then for a fixed volume. So this is a rectangular box, so it would look like this, where it has length, width, and height. I'm just going to use X, Y, and Z for those. So this would be the function for the cost. The cost of it would be, again, there are two surfaces that are top and bottom, but the bottom one costs twice as much, so I'm going to count it twice as much. So XY actually gets a coefficient of 3XY because it's as if there are two bottoms and one top. And then we'll add on the two YZ sides and the two XZ sides. Okay, so that becomes our container, and this is the overall cost, taking into account the condition. There's one other condition here, and that is it has a fixed volume. So X times Y times Z is equal to whatever the fixed volume is. They haven't specified it, so I'll just call it V for now. What I can do then is use this to reduce this from 3 variables down to 2, because I have a technique for optimizing a 2-variable multivariable, but not a 3-variable multivariable. So we're going to use the fact that Z is actually equal to the volume divided by XY, the area of the top or bottom. So I can go ahead and make that substitution, and that's going to change Z into 3XY plus, instead of 2YZ, it's going to be 2V over X. And then the same substitution here, this will be 2V over Y. And now I can go ahead and find the partials that are necessary to do this. So first, I'm going to find CX. And CX, just taking the derivative of this guy with respect to X, is 3Y minus 2V over X squared. And I need to set that equal to 0. I'm going to do the same for CY. CY actually looks the same. It's 3X minus 2V over Y squared, and that also has to be 0. So I've got two equations with two unknowns. If I substitute and use that to solve for the value of X and Y, this is what I get. I get that X is equal to Y, and they're together equal to the cube root of 2V over 3. Now, it turns out that actually is the optimum dimension for those sides, but I can further prove it by looking at CXX. Of course, CXX is going to be equal to 6V over X cubed. And when I plug this in there, that makes 9. I can look at our cross term, CXY. And CXY is just equal to 3. This is a constant. And CYY turns out to be a lot like CXX. CYY is equal to 6V over Y cubed. And substituting in, again, the critical point, we end up with 9. So that means our discriminant is equal to the product of the two double derivatives, and that's 81. And then we subtract from that the value of the cross squared, and that's 9. So this is going to equal 72, which of course is much, much bigger than 0. Not only that, but C double X is positive, and that means this is a minimum. So the critical point is the minimum value we were looking for. And noting that the X and Y coordinate of the minimum are both equal, all I have to do is substitute them in here to find the Z coordinate. When we do that, we end up with the Z value actually being equal to the cube root of 9V over 4. And so that becomes our minimum value in terms of the dimensions, and that is that the x component is the cube root of 2v over 3, the y component is the cube root of 2v over 3, and the z component is the cube root of 9v over 4. Using these dimensions will guarantee that we have the lowest possible cost for the fixed volume v. So once we know the volume of the box, we can plug it in, and that would tell us how big to make each side to guarantee that with this condition of the bottom costing twice as much as the top, the box will have the lowest overall cost.